Look up at the night sky and you are seeing ghosts. The nearest star to our solar system is Proxima Centauri. Even if you could travel at the absolute speed limit of the universe, the speed of light, it would still take you more than 4 years to cross the gap to get there. To map this scale, we have a mechanical problem. There is no physical tape measure, no probe we can stretch across that void. We are trapped right here on Earth. So how do we actually know that star is 4.24 light-years away? Try holding a finger up in front of your face, close your right eye, then open it and close your left. Your finger appears to jump back and forth against the background. Move your finger further away and that jump gets smaller. That optical shift is exactly what is called parallax. If you know the exact physical distance between your two eyes, you can calculate the exact distance to your finger. Astronomers do the exact same thing, just scaled up. Instead of 2 eyes, they use 2 opposite positions of Earth's orbit around the Sun. They take a picture of a star, wait 6 months, and take another picture. This creates a baseline spanning 300 million kilometers, forming a massive invisible triangle pointing directly at that distant star. This diagram illustrates the triangle formed by our orbit. By measuring how much the star appeared to shift against the deep background, we find the top angle, the parallax angle, or AEP. From there, pure trigonometry takes over. The distance simply equals 1 divided by p. This specific calculation is where the standard unit of astronomical distance comes from. When that parallax angle equals exactly 1 arc-second, the distance to the star is exactly 1 parsec, which equals about 3.26 light-years. This geometric method is the bedrock of cosmic mapping. It relies on zero assumptions about astrophysics. It is strictly a measurement of angles. But it has a strict physical limit. Once a star is more than 15,000 light-years away, that parallax angle becomes so narrow that it is simply impossible to measure accurately. To map anything further out than our immediate stellar neighborhood, geometry alone isn't enough. Astronomers had to stop looking at the angles of light and start decoding the properties of the light itself. In 1908, astronomer Henrietta Swan-Leavitt identified a unique group of objects called Cepheid variable stars. Because of a cycle of helium ionization in their atmospheres, these stars swell and contract, causing them to pulse with a steady, rhythmic brightness. This chart shows the direct relationship Leavitt discovered between a star's behavior and its energy. The longer that pulse cycle takes, the greater the star's true energy output, its absolute brightness. By timing the pulse from Earth, we can determine exactly how bright the star actually is. By comparing that known value to how dim the star appears through our telescopes, we can calculate its exact distance. In 1923, Edwin Hubble used Leavitt's method to calculate the distance to a hazy patch in the sky called the Andromeda Nebula. He found it was over 2 million light-years away. That single measurement proved our Milky Way was just one galaxy among many. But Cepheids have their own limits. Beyond 100 million light-years, even these pulsing giants fade into an indistinguishable glow. To measure the true depths of the cosmos, we needed a lighthouse far brighter than a single pulsing star. We found it in Type 1, a supernovae. These occur in binary star systems where a dense white dwarf siphons gas from its companion star. Once the white dwarf reaches exactly 1.4 times the mass of our Sun, the Chandrasekhar limit, it collapses and violently detonates. Because that trigger weight is fixed by the laws of physics, the resulting explosion is strictly regulated. Every time a Type 1, a supernova, happens, it flashes with nearly the exact same peak, absolute brightness. The logic remains the same. Compare the true brightness of the explosion to how dim it appears from Earth. But these cosmic bombs briefly outshine entire galaxies, letting us measure distances across billions of light-years. In 1998, researchers used this method to find that distant supernovae were fainter than they should be. This data proved that the expansion of the universe is accelerating, a discovery that earned the Nobel Prize. By standardizing the luminosity of these dying stars, astronomers established a reliable ruler that spans billions of light-years, allowing us to map the deepest reaches of the observable universe. At the absolute farthest observable edges of deep space, even supernovae are too distant to resolve clearly. Here, we rely on the final tier of the distance ladder, redshift. Think of an ambulance rushing past you. As it approaches, the sound waves compress and the pitch gets higher, and as it drives away, the waves stretch out and the pitch drops. Light behaves the exact same way. This animation shows the stretching of light across an expanding grid. On a cosmic scale, the space-time grid between us and distant galaxies is physically stretching. This elongates the light waves toward the red end of the spectrum on their journey to our telescopes. Astronomers measure this stretch as a redshift value, or Z. If we observe a galaxy with a Z value of exactly 1, the universe has literally doubled in size since the moment that light was first emitted. At this extreme scale, distance is no longer a direct visual observation. Translating that red light into a physical distance requires heavy theoretical models balancing gravity and dark energy. And that brings us to the most pressing paradox in modern astrophysics. When we use our completed distance ladder to measure the expansion rate of the universe, the numbers do not match. We have two highly precise methods. We can calculate the expansion rate using our local ladder of Cepheids and supernovae, or we can calculate it by looking at the ancient radiation left over from the Big Bang. Both methods are rigorous, but they produce two different results. This gap is known as the Hubble tension, and the discrepancy is too large to be a simple calculation error. It suggests either one of our ladder rungs is fundamentally flawed, or that our current cosmological model is incomplete. Resolving this tension is a primary mission for next-generation observatories. Tools like the James Webb Space Telescope are scanning the deep field with unprecedented resolution to find exactly where our understanding of the universe breaks down. We initially set out with a simple goal: to figure out how far away the stars are. While we still lack a perfect answer, the act of building this ruler uncovered the accelerating expansion of the universe and the very limits of human comprehension. The light never lies, we just have to learn how to read it.